video, let's try to understand what are the different types of gradient descents. So before going into this different types, we'll discuss what are the problems with this particular gradient descent. And also while discussing this, we might go through some of the concepts like what is an epoch and what is an iteration and all. Okay. Let's get into this particular video. Let's see what is an epoch initially. Simply for your understanding, I am telling this. One epoch is similar to considering all the training data points that we have. Okay. Whereas what is one iteration? One iteration is same as updation of all the weights that we have. Simply this is one epoch and this is one iteration. Now let's jump into this particular video. So we know what is the formula of gradient descent, that is theta nu equal to theta old minus alpha times loss with respect to the theta. So this we have seen multiple number of times, and now let's discuss what is the problem with this particular gradient descent that we have. Okay, so the main problem with this particular gradient descent is, as we discussed in the last video, in linear or logistic regression, the problem that we have will be very simple. Okay, so either in linear or logistic regression, the problem in our hand is really simple, and the graph of loss with respect to any parameter that we have will be very smooth like this. So if it is very smooth like this, what will happen? It will happen that we'll be having only one minima. Okay, so this point is our minima, and it is only one. And such kind of shapes that we see, those shapes are called as convex shapes. Okay, so in case of convex shapes, we'll be having only one minima. This minima will be both local and global minima. Okay, and our main objective is to reach this particular global minima. So, and gradient descent will completely help us in reaching this particular global minima that we have. So that's why in both linear and logistic regression, this particular gradient descent will work fine. Whereas if you are going on to ANN or any other advanced algorithms, if we check the loss with respect to the theta, so let's say this is our theta, whereas this is our loss. Now the graph will not be such convex shape. Now graph will become more complicated because the problem that we have will be highly complicated problem. So that's why we are trying to build some ANN. So for such highly complicated problem, what happens is, let's say my initial theta value is over here. So let's say my initial theta is over here. So at this point in time, the amount of loss that we are having is very huge, right? So this is the initial loss that we have. So this is the initial loss. At this point, it is showing us the initial loss. And what is the global minima that we are having? So this will be the global minima because it is the minimum of all. Whereas we have lot many local minimas. Like this is one local minima, this is one local minima, this is one local minima, and this is also one local minima, this is one local minima, this is one local minima. Like that, we have lots and lots of local minimas. But in all of these local minimas, we wanted the algorithm to stop at this particular global minimum, right? So this is the main task that we have in case of ANN. But if you are using simple gradient descent, what it does is it will start at this particular loss, and it will smoothly go to this particular local minima, the nearest local minima that it has. This is the main problem that we have with this particular gradient descent. And let's discuss the other problem. This is the main formula for gradient descent, that is theta nu equal to theta old minus alpha times loss with respect to the theta, right? Now, let's say we are trying to solve some regression problem. And in case of regression problem, what is the loss function that we will use? The loss function that we will use is mean squared error. This we have discussed multiple number of times by now, right? So, and what is the formula for this particular mean squared error? That we'll be calculating it like this: 1 by n summation of I from 1 to n y minus y cap whole square, right? Where what is this y? This y represents our actual value, whereas this y cap represents our predicted value. And from where we'll be getting the predicted value? This predicted value we'll be getting it from our ANN. After doing forward propagation, finally we'll be getting our predicted value, right? So we're comparing these two and we are able to calculate the loss. And this, for how many number of points that we are doing? We are doing it for all the training data points that we have. So this is what we are doing in case of normal gradient descent, or we can even call it as batch gradient descent. Okay. So in case of batch gradient descent, we are trying to calculate loss for all the training data points that we have, and then we are updating all the weights. So simply this formula is like this theta nu is replaced by all the parameters that we have, and finally we will be updating all of them, right? So in order to do these updations, we'll try to calculate loss on all the training data points that we have. So simply this is what we'll be doing in case of gradient descent. But another problem that we might face is in case of ANNs, or even complicated algorithms like CNN, RNN, or basically in deep learning, the amount of data that we need is very huge. In order to make the model learn, the amount of data that we require is too much. So it can be in some GBs, or sometimes it can be even in TBs. So when we have such huge amounts of data, what will happen? We need to load all of that data, then only we can calculate the loss, right? So we need to load all of this data onto RAM, and then we need to calculate this particular formula, that is y minus y cap whole square. So this is what will cause problem. And as the data size is huge, we can't directly load all the data that we have in order to update all the parameters that we have. So that is the main problem. And let's say if you are trying to do simple gradient descent, then in one epoch, how many number of iterations we will do? What is one epoch? One epoch is nothing but considering all the training data points that we have. So here, what is one iteration? One iteration means the updation of all the weights. So here, if we are applying this formula, that means that we are updating all the weights. So we are doing one iteration, but within this one iteration, how many number of data points are we covering? We are covering all the n training data points that we have. So that's why in case of simple gradient descent, one epoch is equal to one iteration. Okay. I hope this point is clear. If it is not clear, please comment down in the comment section. I'll try to help you out there. This is about simple gradient descent. And what are the two main problems? One is it can stop at the nearest local minima, and the other problem is it can't load all the data. If it is trying to load all the data that it has, then basically our laptop or system might crash. Okay, so these are the two main problems with this particular gradient descent. And we already seen that in case of normal gradient descent, one epoch is same as one iteration. Now let's see what are the other types of gradient descent that we have. The second type is stochastic gradient descent. So in order to stop the crash, what can we do? So here we are trying to load all the n number of training data points. So instead of doing that, simple strategy is to take only one data point at a time. Okay, so we are applying the same formula, that is theta nu equal to theta old minus alpha times loss with respect to the theta. But here, previously, this loss is getting calculated on all the training data points that we have. But now, loss will be calculated on only one training data point. That is, I goes from 1 to 1, y minus y cap whole square. Okay. So once we get loss on one data point, so based on this loss, what we'll be doing? We'll be updating all the parameters that we have, right? So this formula simply refers to updation of all the parameters. Okay, so If we are updating all the parameters, that means that we have completed one iteration. Simply this formula is nothing but we are doing one iteration. Okay, so within this one iteration, how many number of data points are we considering? We are considering only one data point. So this loss is calculated on only one data point. So that's why we are considering only one data point. So in order to complete one epoch, how many number of data points do we need to cover? We need to cover n number of data points because our training data set size is n. Then in order to cover all these n training data points, we need to do how many number of iterations? We need to do n iterations. Okay. And why do we need to do n iterations? As in one iteration, we are only covering one data point. So in order to cover all the data points, we need to do n iterations. Then only we can say we have completed one epoch. So like this, as we are loading only one point at a time, it will not make a crash on the system, right? So that problem is cleared off. Now let's see the second problem. That is, as I said, initially, let's say we are starting over here. And when we are starting over here, we might smoothly stop at this particular local minimum. But in case of stochastic gradient descent, then we will not smoothly reduce. Our loss will not get reduced very smoothly. It can happen that initially my loss will be over here, but after some time it might go somewhere over here, and then it might go again over here. Like that, my loss will like fluctuate too much. And in this fluctuation, it can happen that it might go on to some better local minima. So we can't say that it will go to the global minima, but most probably it might go to some better local minima. So that is what we can say with this particular stochastic gradient descent. Okay. So I hope uh, what is stochastic gradient descent is clear for everyone. Here we can say our batch size. What is batch size? Batch size is nothing but number of data points that we are covering in one updation or in one iteration. So batch size is equal to 1. Whereas in case of normal gradient descent, what is our batch size? Our batch size is equal to n because we are covering n data points in one updation. Here, one epoch is equal to one iteration, whereas here, one epoch equal to n iterations. Like here, if you observe, we have seen gradient descent, normal batch gradient descent, and then we have seen stochastic gradient descent. So if you see, both these are extremes. There we are covering all the data points that we have, whereas in stochastic gradient descent, we are only taking one data point. So these two extremes are not at all good, right? We need to maintain some good balance between these two. That's why we will go for some other technique, that is mini batch gradient descent. Okay. So in case of mini batch gradient descent, batch size can be decided by the user, that is us or the programmer. So we can decide batch size. Let's say batch size is B. Then our gradient descent formula will remain the same, that is theta nu equal to theta old minus alpha times loss with respect to the theta. And how this loss is getting calculated? This loss will get calculated on B number of points. Okay, I from 1 to B, y minus y cap whole square. So once we cover all the B points, what does that mean? Once the loss is getting calculated on all the B points, then we'll update all the weights that we have. So this formula, I have told you this. This formula means that we are updating all the weights that we have, but that means that we are completing one iteration. And within one iteration, how many number of points we are covering? We are covering B number of points. But what is the number of points that we need to cover overall? So in order to complete one epoch, the number of points that we need to cover is n number of points. So but here we are only covering B number of points. So in order to complete one epoch, what should be the number of iterations? The number of iterations should be n by B number of iterations. So this is the relation between one epoch and epoch and iteration in case of mini batch gradient descent, whereas over here batch size is 1, and this is the relation between epoch and iteration. And here, this is the relation between epoch and iteration. Now, this particular mini batch gradient descent will have advantages of both stochastic gradient descent and also batch gradient descent. Okay. So this is the advantage of using mini batch gradient descent. But in general, either normal gradient descent, that is batch gradient descent, or stochastic gradient descent, or even mini batch gradient descent, these are not like in general, these are not chosen, especially in case of deep learning algorithms. That is because most of the time, in case of deep learning algorithms, the loss function will become non-convex, or we can say concave. So if it is concave, then it can happen that there are multiple local minimas, and let's say our descent is stopping over here, then our mini batch and stochastic gradient descent might stop over here, okay, or stochastic. But this is also not a good solution, right? So that's why we need to go for using some advanced optimizers like like Adam or AdaGrad, RMS prop, Ada Delta. Like these are some of the advanced optimizers, and these we'll be using apart from these gradient descent algorithms. Okay. So in there also everything remains the same. That is theta nu equal to theta all minus something will be there, and this portion will change. Okay, so this portion will change in case of these optimizers, and maybe in the future classes we might discuss these as well. But for now, it is not that important. Just remember that instead of using this MBGD, SGD, and BGD, it is preferable in case of deep learning to use these particular optimizers. Okay, so this is what you should remember, and I hope this particular video is clear for everyone. And if you have any doubts, please comment down in the comment section. I'll try to help you out. And thank you everyone. Bye bye.